In this video, we'll be focusing on conservation of angular momentum, one of the most powerful tools in physics. This concept explains why spinning systems speed up, slow down, or behave unexpectedly during collisions and shape changes. If you master this topic, many rotational problems become plug and play. So, let's review some angular momentum. So, angular momentum, it measures rotational motion, and for a rigid object, L is going to equal to inertia times the angular velocity. So that's your angular momentum there. And for a point mass, we have the formula that L is equal to R times mass times the velocity. And this is valid when the velocity is perpendicular to the radius. So you can represent that like that. So it is measured also in kilograms times meters squared per second. Now let's continue on with the topic of conservation of angular momentum, where angular momentum is conserved if and only if the sum of the external torque is equal to 0, and when this condition is met, Li is equal to Lf. And for rigid bodies, we are able to plug the formula that we had here, which we'll just represent here. We're able to plug in our formula on both sides, and then we have I initial, W initial is equal to IF times WF. So what counts as external torque? The classification includes a couple things. So external torque includes friction with the ground. It also includes applied forces at a distance from the axis. It also includes air resistance, which is usually negligible, though, so in those cases you wouldn't include. And what's not included in torque are internal forces and also forces through the axis of rotation. Another thing you need to know is the difference between energy and angular momentum. So angular momentum is conserved when even when kinetic energy is not conserved, and its angular momentum is also conserved when objects collide or stick together. Now let's continue with some problems. So let's say we have a skater that spins at speed, angular velocity initial with rotational inertia I initial. She pulls her arms in, so her inertia becomes 1/3 I initial. So this is the figure skater. She's spinning like this. Initially her arms are all the way out here, but then her arms go inward like this, and 1/3 I initial. So we want her new angular speed. So check for external torque. So external torque, do we have it? No, we have no external torque. Therefore, we have the conservation of the angular momentum. Angular momentum is conserved. And because this is the case, we can write the conservation equation, which is I initial times W initial is equal to 1 over 3 I initial WF. Then solving this is just WF is equal to 3 times W initial, and we have WF. That is our final answer. So now we can move on to our next question. So we have a small mass moving at speed v strikes and sticks to the edge of a stationary disk of inertia I and radius r. Find the final angular speed. So the angular speed, that's going to be W. So we're trying to find WF. The mass is moving at, okay, so it strikes the edge, so it's going to be on, we'd say like it's on the rim, kind of right at the edge. This is of mass m, and it was moving at, we can just imagine it's being shot from this angle or just from this direction. Has the radius r, and we want to symbolically represent this. First, we check for external torque, so there is no external torque. And because there's no external torque, angular momentum is conserved, just like before. And now we're going to find the initial angular momentum, and Li initial is going to be equal to the radius times mass times velocity, which is going to be mv capital R, which was the radius in this case scenario. Now the final angular momentum, Lf, is going to be equal to 1 plus mr squared times wf. Now setting these two equal, we have Li is equal to Lf from conservation right there. So we have mvr is going to be equal to 1 plus, or I plus mr squared times wf. We just want wf, so we divide both sides by I plus mr squared, and then we have mvr divided by 1 plus mr squared as our final solution. So what we can take away from this is kinetic energy was not conserved, but we saw that angular momentum is conserved. Now, let's move on. A particle of mass m moves in a straight line with speed v, passing a pivot at a closest distance d. Find its angular momentum about the pivot. So we have our particle m, and here's the particle. It's moving and it's passing through a pivot, which will represent here, at the closest distance of d. So at its closest distance, it's going to be at d. So the momentum is also applied perpendicular. So then here the momentum is going to be perpendicular to r. And then from that, we know that sine of theta is equal to 1. Therefore, we know that L, your angular momentum, is just going to be equal to m times v times t. And from what we can take away from this is that an object doesn't need to rotate to have angular momentum. Now, we can actually write down some formulas that we can take away from just these problems. So again, angular momentum, let's have a quick review. Angular momentum is going to be of a rigid body. This is going to be L is equal to IW. You use this for spinning objects. And this is angular momentum for a particle. This is used for collisions and for flybys. And Li is equal to Lf. This is when you have no external torque again. And then rotational collisions we'll use this, rotational collisions, and energy versus momentum. Remember, momentum can be conserved and energy is not. And when that happens, when momentum is conserved, energy not conserved, that's an inelastic collision. So now let's continue with some more practice problems to exemplify these principles. So a uniform disk of rotational inertia I rotates at an angular speed initial. A thin ring of inertia 3I is gently placed on top and sticks, no slipping. Find the final angular speed. So we know we have this disk, right? So let's just draw this at the disk, right? So, and then we have a ring on top of it. The ring on top of it is going to be like this, and the ring on top of it, the uniform disk. Okay, so let's actually color the disk a different color. The disk, we're gonna just make that purple, and then this, I'll just make this pink. So this disk is going to rotate at W initial, and then the thin ring, it has an inertia of 3I, and then it's gently placed on top and sticks. So if it sticks, that means it's perfectly inelastic collision. That means you have conservation that we can use. So now let's check for external torque. There is no external torque, and that's because the axial friction is negligible, and so that means we have conservation of angular momentum. And now we can write the initial. So we have Li initial is equal to I times angular velocity initial, and then the final is going to be, we want to find the final inertia, and that's going to be the initial inertia plus 3I, which was, so this was originally I, and then you combine the two, we have 4I, and then LF is going to be IF, WF, and that's going to be 4 times I times WF. As we know that this, we have 4 times the amount. So that's, now we can use conservation. Li is equal to LF, and because of that, we can write IWL initial for I angular velocity final. Solving for just WF, that's just going to be W initial divided by 4. Now we have a sliding mass lands on a rotating disk, but energy is not conserved. So a small mass M slides without friction at speed v and lands on the rim of a stationary disk, radius r, sticking at the edge. Find the final angular speed. So it's a disk, and it lands without friction. There's no friction, and it lands at the rim. So, and it has the disk, it has a radius of r, and then it also has an inertia of I. So we want the final angular speed. That's going to be it's going to be WF. So let's see. We know that we have we're looking for external torque about the center. Well, there is none. There's no external torque because it was a brief collision. So now we can conclude again that angular momentum was conserved. So now we can find the initial angular momentum. So we have Li is equal to RMV, is equal to RMV. This was a point mass, And then it was also a tangential impact because of this. No, we can, now we can write LF is just I plus mr squared times the angular velocity final. So then the final, now you can set them equal to each other. Li is equal to LF. You have RMV is equal to I plus, make that a little more clear, I plus mr squared times WF. WF is equal to MVR I plus mr squared. Now let's continue with another problem. So let's say we have two masses on a rotating rod where the axis is through the center. So two equal masses m are attached at ends of the light rod to L rotating about its center with angular speed, angular velocity initial. The masses slide inward to positions half of L from the center. Find the new angular speed. So two ends of a length 2L. So one mass here, you have another mass here, and you have M, so they slide inward. So we can make a second drawing below this. They slide inward to positions half of the length to the center. Oh goodness. Okay. So this is length L, and then this is length L over 2. We want the new angular speed. So we have to check for external torque. There was none, so there's means we can deduce that angular momentum is conserved. And because of this, we write the initial inertia. I initial is equal to 2ml squared. And we have the IF is equal to 2ml over 2 squared, which is, you can square that will just be 4, and then 2 divided by 4, that's still going to be 2. You have ml squared. Now we can write the conservation equation. Again, I initial is equal to IF, or sorry, we'll have L initial is equal to LF, and then you have I initial angular acceleration, IF, angular acceleration again. Now, substituting in our values, we have 2ml squared W initial is equal to ml squared divided by 2 WF. Now we just have WF dividing both sides by ml squared divided by 2. We have 4W initial. That's because we can show our work for that actually. So you're going to multiply this side by 2, and then you're multiply this side by 2. ml squared divided by ml squared. So yes, you just have 4, and then you have ml squared canceling out over here. So yes, that's gonna be your answer. Now let's say we have a question about a particle that passes a pivot at an angle using L equals RP sine theta. A particle of mass m moves with speed v past a pivot point. At a given instant, its position vector makes an angle theta with its velocity, and its distance from the pivot is r. Find the angular momentum magnitude about the pivot. So what you're going to do is you're going to use the definition for a point mass, which has been L is equal, your angular momentum is equal to RP sine theta. And also using momentum, we have P is equal to mv. And now we can substitute Pn right there. So then you just have L is equal to RMV sine of theta as your solution. Now we can move on to our next question. A person walks radially inward on a platform from our radius to radius half divided by 2. The platform person system has no external torque. By what factor does the angular speed change? Can draw this out visually. So the person is here originally. This is the radius, and then this person moves to, so this entire length is the radius, and then this person it moves to r over 2. They move to r over 2. So conservation condition, we have no external torque, therefore we have conservation of angular momentum. We have Li equal to Lf. So model, we can treat the person is contributing I equals to mr squared to the total inertia. So we know that I initial is going to be proportional to the radius squared by looking at this on both sides of the equation. So therefore we know that IF is going to be proportional to r over 2 squared, and then that's r over 2 squared, that is just r squared divided by 4, because finally we know that, well, we know initially, see, it's at radius r. We know finally it's at IF. So now we want to find, well, we can use conservation and write that out here. Initial IF WF using conservation. Now we just solve for WF, which is equal to 4WI, and then we can see that it's being scaled by a factor of 4. Therefore, we have that the angular speed increases by factor 4. So let's move on to our next problem. A particle moves in a straight line with a constant speed. Is its angular momentum the same at about all points in space? So it's moving in a straight line at a constant speed. And we want to know about its angular momentum L. So we have to remember that angular momentum, it depends on the choice of axis. That's the most important thing. So we use the formula L is equal to RP sine theta, right? So then if you have different axes, right, that means you have different perpendicular distances are perpendicular. Therefore, the angular momentum always varies with your chosen reference point. Well, it makes sense because, like, if you're measuring something from a different perspective, it's going to have a different angular measurement, different radius, it's going to have a different angle, so it's going to be different. So that means the angular momentum is different about all points. All right, thanks for watching.